Welcome back. This is the second video in our Center of Gravity video series. We have 4 videos in the series. Hopefully you've already seen the first video, which gives you a little bit of background on center of gravity and some of the rigging terminology that I use throughout this video series. Again, we're really focused on center of gravity as it relates to rigging and lifting overhead loads. Normally I'm talking about a crane, but it could be other types of lifting equipment also. In this video, we're going to focus on 2 methods for finding the center of gravity of a load, if the load is an odd shape or if it has an uneven weight distribution. That's really where these methods are useful in those situations. We'll talk about the trial and error method, and then we'll talk about the straight line method. All right, let's talk about 2 methods for finding a load center of gravity. Like I said in the introduction, these are methods you would use if it's an odd-shaped load or a load with an uneven weight distribution. The types of loads where the center of gravity is not squarely in the middle. If we're talking about a perfectly symmetrical load with even weight distribution, you can pretty much pinpoint the center of gravity without any special methods or any use of mathematics. But these are methods when you don't have those kind of loads, when you're working with the odd loads. Talk about the trial and error method, which I'm not a big fan of, but it's widely accepted within the crane world. Then we'll talk about the straight line method. One sidebar, one note. When you get into these types of loads, where it's not easy just to pinpoint, look at a load and say, there's a center of gravity. When you get into these types of loads, if your company has engineers, get them involved. They are going to be the most qualified people within your company for doing the calculations necessary to find the center of gravity. If your company does not have engineers, you may want to work with an outside engineering firm to have them help you with your rigging design. If it's a complex object, complex lift, it may be worth the money, the investment, to get that outside engineering firm involved. Having said all of that, engineers should be the ones doing this. Having said all that, safety pros should understand how to find the center of gravity for moderately complex loads, like the ones we're going to be looking at. Once you get beyond that moderately complex system load type of situation, that's where you want to use your engineers for sure. Preferably, the engineer that you're working with is going to be a registered professional engineer, meaning they've taken exams, they've received a license. They are the best of the best in the engineering world. As a sidebar, just terminology as you get into the work world, you'll hear people talking about, well, he's a PE or he's not a PE or she's a PE. PE is the abbreviation for registered professional engineers. Most people aren't going to use RPE as the abbreviation, or they're not going to use registered professional engineer every time they're talking about a PE. PE is just a common lingo in the construction world and in other industries also when talking about a registered professional engineer. All right, well, let's jump into the trial and error method. First of all, again, least preferred method, but it is accepted in the crane world. Low tech, there's no math involved. Like I said, widely accepted method in the crane and heavy lifting industry, and it's simply trial and error. And here are the steps that you would follow if you were using this method to find your center of gravity. First of all, you would estimate what you think is the approximate center of mass or center of gravity for the load. You take a look at the load, you know a little bit about the load, and based upon your knowledge and your observation, you make a guess as to where the center of mass is going to be for that load. Then you develop a rigging design based upon your estimate, based upon your guess of where the center of gravity was going to be. You develop a rigging design. You make the connection. You connect the crane to the load with the rigging components. Then you slowly lift the load until it breaks contact with the supporting surface. At this point, once it breaks contact with the supporting surface, you should have a pretty good idea of how close your guess was. You want it just high enough to see how the load is hanging. Is it hanging level? If it's hanging level, you did a good job of guessing the center of gravity and developing your rigging design, and you're good to go. But most of the time when you're using the trial and error method, the first time around, based upon your guess, when you lift the load, it's not going to be hanging level. There may be some swinging. There may even be a sign of that it's wanting to spin because of it's out of level. If that's the case, then you need to lower it and adjust your rigging so that you do get that crane hook directly over the load center of gravity. What we see in the picture here is an out of level load. In this particular example, or a load like this, you could return that load to level, or one of the adjustments that you might be able to use is just adjusting the length of the sling legs to level out the load. And we'll be talking more about that in subsequent videos, how to adjust the rigging so that your hook is over the center of gravity and your load hangs level. Sidebar, in this operation that we're seeing here, it looks like a roof panel that they're lowering into position. It's possible that this was purposefully rigged in this position to make it easier to set the wall panel or roof panel or whatever it was. And that is okay, as long as the rigging design takes everything, all the variables into consideration. You don't want to haphazardly go at this because you want the load in a certain configuration. You need some planning behind it, some thought behind it. In some cases, maybe some mathematics behind it, using your engineer. But there are certain situations where it's okay for the load to be in this position. Now, I don't know a lot of the background on this load, but my guess is somebody on the ground hooked it up and it was what it was. They didn't give a lot of thought to keeping it level or keeping it vertical. They just wanted to get the load up there, and this was the result of their rigging attempt. There are limitations to the trial and error method, as I'm sure you can anticipate. It's only really good for simple loads, lightweight loads. If you have heavy, more complex loads, trial and error is going to be very time consuming to try to, you may spend an hour and a half just trying different configurations to try to get it to sit properly the way it's supposed to without swinging and be in that level position that you want it in. One tool that you can use to make the adjustments easier when you're using the trial and error method is an equalizer beam, also called an adjustable spreader. When you lift it that first time and it's not hanging level, you can use the equalizer beam to make a slight adjustment and get closer to level. And we can see over here in this diagram to the right side within this diagram, we see a load where the pick point, illustrated by that hook, is not in line with the center of gravity and it's hanging out of level. Actually, it is in line with the center of gravity, but it's out of level because when they started the pick, this was not over the center of gravity. To correct this problem with an equalizer beam, they just slide their pick point over one way or the other so that the pick point is over the center of gravity when they start the lift, and they're able to maintain level throughout the lifting operation. There are many examples of adjustable spreaders. Here's another example of an adjustable spreader beam that could be used when you need to make slight adjustments to get your load to hang level and not swing or have any other unintentional movements. As a sidebar, rigging in general, a single leg vertical hitch like we see here is not a good idea with odd shaped loads or loads having an uneven weight distribution. If it's a simple symmetrical load and everything's distributed equally, you can get by with a single vertical hitch configuration like we have here in the picture. But if it's an odd shape uneven weight distribution, you need more legs in your rigging design. That more legs mean more stability, but you don't want to make it overcomplicated. You want it just as complicated as it needs to be to stabilize and control the load. Yeah, that would not be a good setup that we have there. All right, well, that's a trial and error method. Let's talk about a straight line method, or the straight line method. I'm going to give you a couple of alternatives mathematically for arriving at the location for the center of gravity using the straight line method. The straight line method, before we get into those two different mathematical alternatives, this is what we're going to use if we have relatively simple odd shapes with an uneven weight distribution. Or it could be an odd shape or an uneven weight distribution. You could have an odd shape like we have with this L-shaped or backward L. All the weight's equally distributed, but it's an odd shape, which makes it hard to look at and determine the center of gravity. Or it could be a load where it looks symmetrical, looks like a perfect rectangle, but one side is heavier than the other. That's what we mean by uneven weight distribution. This is really best, but it's really only useful. It can't be used except in this situation where you have different component centers of gravity lining up in a straight line. All of your different components and their centers of gravity need to line up in a straight line to use this method. It's usually going to be best when there's only two component centers of gravity, but it can be used if three or more centers of gravity line up. I'm going to do two examples. The first example, we have two component centers of gravity. The second example, we have three, where they all line up, and you can use this method. And if you're not sure what I mean by component centers of gravity, I'll explain that as I move along. This method, I'm not going to get a lot into the concept of moment. We've talked about moment in other classes. Moment is force or mass times distance, and you'll see the formula written out a couple of different ways. M for moment equals little m for mass and x for distance, or m for moment equals force times distance. And we're not going to get a lot into moment in these videos, but this method and the method I'm going to talk about in the third video is based upon the concept of moment. Force moving around a fulcrum, which is impacted by the mass and the distance from the fulcrum. Yeah. Having said that, no more about moment, except for maybe in the third video. But for now, I just wanted to throw that out there. We're really talking about center of gravity being determined by mass of the object and distances from a point within that particular object. This is a good example of the type of object where we can use the straight line method. We have an L-shaped object with uniform density, meaning it's the same material, just got a funny shape that makes it hard to just pinpoint the center of gravity. Another concept that I want to throw out here that I'll use periodically in this video and the third video, point mass. For our purposes, we can think of that as another term for center of gravity. A lot of times you'll see the term point mass used with more complex objects that are divided into sections, and each section has a different center of gravity or point mass. And this is really what I'm talking about when I talk about component center of gravity. We're talking about breaking the object down into sections, and each section has its own center of gravity. Think of each section as a separate component in the object, with each section having its own point mass or center of gravity. Right, well, let's go ahead and look at a problem here. We have this object that we want to lift. First thing we need to do is break it down into sections, break it down into components. We have section 1, section 2. We need to calculate or find the weight for each of the sections. Sometimes you have to do the calculation, a separate calculation to find the weight. In this example, we know the weights, we looked up the weights wherever. And we know that section 1 weighs 4,000 pounds. Section 2 weighs 12,000 pounds. Now we want to locate the center of gravity for each section. Now, once we break it down into these two components, they become simple symmetrical objects with an even weight distribution. So we know that the center of gravity for section 2 is going to be somewhere in here, right there in the middle. Same thing for section 1. So section 2 center of gravity, section 1 center of gravity. Next step, draw a line between the centers of gravity for each section. There's our line. There's the straight line method thing coming into play. Now, if we were doing this with a real object, we're going to measure the distance of this line. For our example here, we have a 7-foot distance between the center of gravity for section 1 and the center of gravity for section 2. Now we divide the weight of section 2 by the total weight of the object. Total weight of the object, 16,000 pounds. We divide 12,000 by that 16,000 pounds. We come up with 0.75. Now we multiply the distance between the centers of gravity by 0.75. So we end up with 7 feet times 0.75. And our center of gravity is 5.25 feet from the center of gravity for object 1 along this line. Now note, when we were dividing the heavier section by the total weight of the object, this is giving us a weighting factor that we're using to identify the object center of gravity. Another notation, I've already mentioned this. This is the kind of load where you might be able to use the trial and error method. A lot of companies do this. A lot of riggers do this. I would rather see them, getting out their calculators and doing some calculations to be more precise with identifying the center of gravity. Again, this is not that difficult. Simple steps, just some division and some multiplications, all that's required to find a more precise location for our center of gravity. Again, this is one example of the straight line method. You can think of this as maybe the more commonsensical approach to the straight line method. Now we're going to use the more mathematical approach to the straight line method. And for me, this is my preferred method. And we can use this, I can do it this way, but I prefer to do it this way. And when you're doing this for real, or if you're doing this on a certification exam, it's up to you. On the certification exam, this method's probably easier because you don't need to remember a formula. You just need to remember the logic of what's going on here. With this method, the more mathematically oriented method, you do need to remember a formula. We're still breaking it down into components. Section 1, 4,000 pounds. Section 2, 12,000 pounds. We're still locating the center of gravity. We're still drawing our line. So again, we're still straight line method. But what we're doing with the line now is a little bit different. We're going to bring this line over to the side, and we're going to put it next to a number line. Okay, we've measured the line and it's 7 feet. We have our line up here. Now we have a number line going from 0 to 7 alongside it. Once we have the weights of the components and we have this number line, we can then use this formula to find X sub CG. And X sub CG is the object center of gravity. Again, X sub CG is the calculated center of gravity or center of mass. Little m is the mass or weight of each component. X is the location of each component. And we're using this number line as our method for assigning a location, a relative location to these centers of mass. And one thing about this number line scale, we're using 0 through 7. That's the simplest, the most straightforward method if we have 7 feet between our centers of gravity. But you could start at 10 and go to or you could start at 0 and go 10, 20, 30, 40, 50, 60, 70. That would be fine. You'd get the same answer. Or you could put 0 on this end and 7 on this end, and all of your locations would be negative numbers. That would work as well too, as long as you're consistent with your measurement system, the number scale that you're using. And I will show you that in an example coming up, how the number line, we have some leeway in how we use our number line. But always go with the easiest method. I'm just throwing that out there because there are options. But the easiest method, the easiest number line in this situation, 0 through 7. So, hey, let's plug numbers into this formula. M sub 1 is the mass for 1, 4,000 pounds. Okay, X sub 1 is the location of the center of gravity for section 1. It is sitting at 0. So X sub 1 is equal to 0. Now we want to do the same thing for M sub 2 and X sub 2, which is the center of gravity and location for section 2. M sub 2, 12,000 pounds. Then X sub 2 is the location, 7. Once we get these numbers entered in the numerator and the denominator, which I'm trying to get ahead of myself, the denominator, M sub 1, is 4,000, M sub 2 is 12,000. Once we get all these numbers in here, it's as simple as some multiplication, some addition, and some division. And then we'll have the location for our center of gravity. Go back to this formula just for a second. With the way the formula is laid out, M sub 1, X sub 1 plus M sub 2, X sub 2 plus ... plus M sub n, X sub n. This is really telling us that we can use an infinite number of points if they are lined up in a straight line. Same thing below. We could have 4 points, 5 points, 6 points if they're lined up in that straight line. And we can find the center of gravity. Below, same thing in the denominator. We can have multiple components with multiple masses that we're working with. This example, we just have 2 component centers of gravity, and it's relatively simple. So let's go ahead and do this math. 4,000 times 0 is 0. 12,000 times 7 is 84,000. Then we have 4,000 plus 12,000 is 6,000. The 0 disappears. We don't need that. We bring everything down. We end up with 84,000 divided by 16,000. And if we did this right, it should be 5.25 feet. But I'm going to bring my calculator up here just to make sure I do it correctly. We got 84,000 divided by 16 and 5.25. So we did something right. Our center of gravity is 5.25 feet from the center of gravity for section 1. Our object center of gravity, or system center of gravity, 5.25 feet from the center of gravity for section 1. So there we got it. So 2 different methods, same answer. Either method will work fine with this type of problem. All right, let's look at another example where we have 3 components. I come from the bridge construction industry, and this was a pretty common scenario where we would have a steel girder with multiple components, and section 1 of the steel girder was connected to section 2 of the steel girder with splice plates and bolts. Most of the time, everything, the 2 girder components are going to be the same weight, but occasionally run into a situation where one of the components is heavier than the other components, and that's what we have here. So here's our problem. What is the center of gravity of a spliced steel beam assembly consisting of 2 beam sections, splice plates, and splice connector bolts? Section 1 is 50 feet long and weighs 400 pounds per foot. Section 2 is 50 feet long and weighs 350 pounds per foot. The splice plates and connector bolts weigh 850 pounds. Don't want to forget about that 850 pounds because that could throw us off a foot or so either way when we're finding our center of gravity. But those are the three components. We've got Section 1, Section 2, and we've got our splice plates and splice bolts. Those are the three components that we're going to be working with, and we're going to use the same formula that I used in the previous example problem. A little more information, lay out a little more information about the setup we have here. Section 1, 50 feet long. Section 2, 50 feet long. There's our center of gravity for Section 1. There's our center of gravity for Section 2. And these are, if we look at each section individually, they're symmetrical with an even weight distribution. So the center of gravity is going to be right at the centroid of the object, that geographic center of the object. Splice plate, same thing. Center of gravity for the splice plate is, and the splice plates and bolts right in the middle. The center of gravity for Section 1 is 25 feet from the end of Section 1, and it's 25 feet from the center of gravity for the splice plates. Same thing on the other end with our dimensions. Everything's symmetrical once we get it bolted up together. The curveball in this is the weight of Section 1 is heavier than the weight of Section 2. And that's why our center of gravity is not going to be right in the middle. If our weights were all the same, center of gravity is going to be right in the middle, but they're not. So we've got to use this formula or another method to find the center of gravity. This is probably the most important measurement of anything on the slide right now, the 50 feet between the center of gravity of Section 1 and the center of gravity of Section 2. That's going to establish our number line that we're using when we're using this method. And like before, we had a number line that went 0 to 7. We need a number line here that goes 0 to 50. But to show you how you can play around with the number line, I'm going negative 50 to 0. And it's all going to work out the same way. Not any problem with the number line being scaled the way it is in this example solution that I'm giving you. They don't tell us exactly what the weights are for each section, for each beam section. They give us the weights for the splice plate, but not Section 1, Section 2. We have to calculate those. The weight for Section 1 is going to be 50 feet times 400 pounds per foot. 50 feet, 400 pounds per foot. For Section 2, it's also 50 feet long, but it weighs 350 pounds per foot. So we have to do some preliminary calculations to get our component weights. 50 times 400, 20,000. 50 times 350, 17,500. And then our splice plate weight is given to us. So all of these three weights together give us our total object weight of 38,350 pounds. Again, 20,000 pounds, Section 1, 17,500 for Section 2, 850 for the splice plates. Now we have everything necessary to use this formula to calculate the center of gravity for this load, for this object. Okay, M1, M sub 1 is 20,000. That's the mass for Section 1. X sub 1 is the location for Section 1's center of gravity, negative 50. Then moving from left to right, and the order doesn't have to be this way, it's just the most sensible. You start from the left and you go to the right in order. Next we look at the splice plate. That's going to be M sub 2. The mass for M sub 2 is 850 pounds. The location for X sub 2, or the location for the center of gravity, is going to be negative 25. Section 2, the mass is 17,500 and the location is 0. Then in the denominator we have mass for section 1, 20,000, section 2, 17,500, and then section 3, or the splice plates, 850 pounds. Now we just need to do these calculations and we'll find our center of gravity. 20,000 times negative 50 is 1,000,000. 850 times negative 25 is negative 21,250. Then 17,500 times 0 is 0. So it's not even brought down because it zeroes out. Then in our denominator, 20,000 plus 17,500 plus 850, we end up with 38,350 as our total mass for the object. When we add 1,000,000 or negative 1,000,000 to negative 21,250, we end up with negative 1,021,250. Bring our 38,350 up. Now we do that division. Bring my calculator back in here. Negative and our location is negative 26.63, and I did round there. Let me go ahead and show you what I round from. It was negative 26.629, and we rounded it to 2 decimal places. We'll just call it negative 26.63. And that's all in reference to this number line scale that we're using. So negative numbers, we're going to go to the left of 0, and our center of gravity is going to be right in here, negative 26.63. And there she is right there, negative 26.63. And if we want to provide another reference point for this measurement, it's 48.37 feet from the end of section 1. That's our center of gravity for this load. So if we're rigging this load, we want the hook of our crane, of our load block, directly over this location on the beam. If we're a little bit left or right, it's not going to hang evenly, which can cause problems, which can cause some serious problems when you're dealing with beams that weigh 35, 40,000 pounds, or even 200,000 pounds, or even heavier in some cases. So that's an example of the straight line method where we have 3 components. And you can use this method with multiple components as long as they're basically all lining up in a straight line. If they're not lining up in a straight line, you got to use another method that we'll talk about in the 3rd video. Now there's one other thing I want to show you here. I know this video is getting long, but it's still shorter than a regular class period. So this is another way of determining the center of gravity for a problem like we just had. In fact, it's exactly the same problem. Center of gravity for a beam assembly. Exact same numbers and everything. This is the method that a rigger might use if he doesn't know anything about the formula that I showed you in the previous example. This is just the rigger going out and figuring it out. They know that the center of gravity is the point around which the weight of the object is equally distributed. They know that. And they know they want to be over that balance point. And some riggers will call it, well, we need to find the balance point of our load. The balance point of the load is the point that will allow the load to hang level. They may not use the term center of gravity, but they know that they want the same amount of weight on both sides of that balance point. So what they're going to do is find the total weight of the beam assembly and divide by 2. And that tells them that they need this amount of weight on both sides of that balance point, or that center of gravity. After that, they're going to use the weight per foot values to find the distance from the heavy end, to find their balance point or their center of gravity that they need to be working with when they're putting together the rigging. And we have 100-foot assembly, 50 feet two 50-foot sections, splice plate in the middle. There's no centers of gravity that for section 1 and section 2 that they're working with. There's no splice plate there's no center of gravity for the splice plate. This is the information they're using with. They do have the weight information. They calculate the total weight for the beam assembly. Then they divide that by 2. 19,175 is what they end up with. They know that on either side of this balance point, they need 19,175 pounds. They'll then calculate the distance from the heavy end by dividing 19,175 pounds by the pounds per foot for section 1. So it would be 19,175 divided by 400 pounds. That's the pounds per foot for section 1. They come up with 47.93 feet as their center of gravity for this load. Now remember what we came up with using the more drawn out mathematical method with the formula, which that's the way I'm going to do it. But you get very close using this Riggers figure it out method also. Just using some logic, thinking through the problem, understanding the concept of balance point or center of gravity. And I keep using balance point because that's what a rigger without a lot of schooling is going to call the center of gravity, that balance point. But this is what we found using the mathematical method that I showed you in the previous slide. We came out at 48.37 feet. There's only about a 5-inch difference between that method and what the Riggers figure it out method ended up with, which it's not exact. I'm all about exact and precise, so I'm going to use the mathematical method. But if a rigger's doing this out on the job and he's within 5 inches and he has to just make a slight adjustment to his pick point locations because he was just 5 inches off, I'm okay with that. I'm not going to beat up a rigger that goes to the trouble of thinking this through and doing some calculations. If they're coming up within 5 inches, kudos to them, pat on the back to them. Not exact, but very close, and it can be adjusted. We're kind of reverting to the trial and error method at that point. So. All right, summary. Again, apologize for the long video. We talked about the trial and error method, and then we talked about, I've got simple component method, straight line method is the better term for that. You'll hear it called the simple component method also. So trial and error method, the straight line method. We looked at the straight line method without formulas, where you're thinking it out, and then we looked at the method with this formula here, which to me, because it's more precise, it's more exact, that's my preferred method. But the think it out approaches, the Riggers figure it out method, or some of the other think it through approaches that I showed you, those work also. All right, that is it for this video. Let me know if you have questions. You got my phone number, you got my email, you got what else you got? Now that's enough. You can get a hold of me if you need to contact me with any questions.